Welcome students. I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dongar College, Bikaner. Today I am going to deliver my lecture on classical mechanics. In my previous lecture of classical mechanics, I have discussed technique of calculus of variation. So briefly, I am going to discuss what is this technique of calculus of variation. For this purpose, we are given a function f. Its dependence is on y, y0 and x. Here x is an independent variable and y0 is derivative of y with respect to x. That means y is dependent variable. For this function, we are defined an integral I to be integration between x1 and x2. These x1 and x2 are respectively the initial and final point. Integral between x1 and x2 of function with respect to dx. This integral is given to us that it has a stationary, that means extremum value. That means this integral can either be maximum or it can be minimum. Now since I is extremum, so students, its variation will be equal to 0. That means del I, this must be equal to 0. So we are given I to be extremum, or we are given that del I is equal to 0. And in my last lecture, I have determined for what value of y this condition will be satisfied. We have found out that condition is del f by del y minus d by dx del f upon del y naught. This must be equal to 0. Now, on this variational principle, on this basis, we can solve many problems. Today, I will discuss these problems. First of all, we are given a problem. In this problem, I am given 2 points, initial and final point. Students, what we have to find? We have to find the shortest distance between these 2 points in a plane. Now, we already know that shortest distance between 2 points is a straight line. So we will derive that shortest distance between these 2 points will be straight line. For this purpose, I am taking a small arc of length ds, and what is ds? Since we are in a plane x and xy plane, so ds will be under root dx square plus dy square. This will be the length of this small arc ds. I am taking dx common. So taking dx common, it will become 1 plus dy by dx whole square. Why I am taking dx common? Since we know that our function f depends on y, y0 and x. So I am expressing this in terms of I am finding my function f, and for finding my function f, I have to find its dependence in terms of x, y and y0. So I have taken dx to be common. Now I am writing dy by dx to be y0. So my ds will be equal to dx under root 1 plus y0 square. I have now taken only a small arc which is of length ds. I have to find the total length of the curve between initial and final point. So I am summing this and summing in terms of integral. Integral I will be between initial and final point, and integral will be of small arc ds. Substituting the value of ds, I find the value of ds to be equal to under root 1 plus y naught square dx. My function f is root 1 plus y naught square. I have already determined the condition for y to be extremum as del f upon del y minus d by dx del f by del y naught equal to 0. So to solve this expression, I have to find differentials. First differential is del f by del y. Since f does not depend on y, this term is equal to 0. And del f by del y naught, differentiating f with respect to y naught. Because there is a y naught term, f depends on y naught, I get the differential as y naught upon under root 1 plus y naught whole square. Substituting these two values, my equation will become, this is 0 d by dx. This term I have already found out, and this in this side I have 0. So integrating it, I got y naught upon root 1 plus y naught square. This will be equal to constant of integration. I have written as constant to be r. Now I am cross multiplying these terms and squaring. I get y naught square. This will be equal to r square multiplied by 1 plus y naught square. Collecting the terms of y naught square, I get this term. Now since y naught square is equal to r square upon 1 minus r square, taking under root, y naught will be equal to under root of this term. What is this term? R, which is constant. 1 is also constant. So students, this side will be equal to a constant term. I am assuming this constant to be equal to a. So y naught equal to a. What does y naught means? Y naught means dy by dx. So integrating the y naught term, I will get y. Y will be equal to ax plus b. Is constant, b is constant of integration. Students, we know that what is y equal to mx plus c? It is an equation of straight line. So solving my expression, I got the equation of straight line. So I was given a problem in which I was supposed to find what will be the shortest distance between the 2 points. We have derived that shortest distance between the 2 points will be a straight line, which we have derived by the expression y is equal to ax plus b. In my next problem, what I have to find? I have to find the minimum surface area of revolution. What I have given? I am giving you a curve. This is the curve which passes through two endpoints. Initial point being x1, y1. Final point being x2, y2. It is placed in xy plane. Now what I am doing, I am rotating this curve about this y-axis. That means this curve is revolving about this y-axis. What I have to find? What will be the minimum area that will be formed by this curve on revolving about this axis? I have to find the shape of the curve. Now in this problem, I have to find the minimum area. That means we have to find the condition of extremum. So here also we will use the variational principle, because in variational principle we are given that I integral is extremum or delta I we are given is equal to 0. As in my previous problem, initially I have determined the length of a small strip. And to solve the problem, we have summed the total length of the strip in terms of integral. We will use same approach here. For this purpose, I am considering a point A and dividing this whole area into small strips. At point A, the distance of this point A, that means distance of this curve from the axis of rotation, let it be equal to x. Now, since this curve is rotating about y-axis and the distance, which is the radius of the curve, is x. So distance covered will be equal to circumference, but that means distance covered will be equal to 2 pi x. And we are assuming that at this point, let this strip has a width which is equal to ds. So at point A, the surface area of strip will be 2 pi x circumference into the breadth of the strip, which is ds. And in the previous example I'm showing, we have already determined ds. What is the value of ds here? ds is dx under root 1 plus y naught square. Because in both the problems, we are solving in xy plane. So students, I am substituting the value of ds here to be under root 1 plus y naught square dx. And here I have taken only the area at point A. We have to take the total curve. So to determine the total surface area formed, I am going to integrate this surface area of strip between initial and final point. The total surface area, students, will be integral from initial point 1 to final point 2. 2 pi x under root 1 plus y naught square dx. And this total surface area will be minimum, or del I will be 0. For this purpose, we already know that the equation that must be satisfied is differential equation second order. The second order differential equation which must be satisfied is del f by del y minus d by dx del f by del y naught equal to 0. This 2 pi is constant. Function f. This is my function f. F is x under root 1 plus y naught square. To solve this expression, we have to solve my differential del f by del y. Since there is no y term, differential will be 0. Now I am going to solve the differential with respect to y naught. So differentiating with respect to y naught, x is constant, and the differential of under root 1 plus y naught square, it will be half 1 upon 1 under root 1 plus y naught square, 2 y naught, 2 cancels with half. So I get the differential of f with respect to y naught. Substituting the two values, and on integrating this expression, this differential cancels out. I get my term to be x y naught upon root 1 plus y naught square and a constant of integration a. Now we have to find out the minimum surface area of revolution is followed by which type of curve. So I'm going to find my curve that must follow the condition of minimum integral. For this purpose, I'm going to square this term and Squaring this term, I get x square, y naught square, 1 plus y naught square equal to a square. Now collecting the terms of y naught square, I got my term. Since here we have y naught square, so taking the under root, I get y naught is equal to a upon root x square minus a square. On integrating, what is y naught? Derivative of y with respect to x. So I am integrating with respect to x. Integral, it will give me value of x, y, a is constant, taken outside, integral of dx upon under root x square minus a square plus b, constant of integral. Using the standard integral, I have got the value of y to be y is equal to a cos hyperbolic inverse x upon a plus b. I get x is equal to a cos hyperbolic y minus b upon a. Students, I got my value of x. I got my required path. This is an equation of catenary. What is catenary? Students, you might have seen the chain near some parks. The shape which that chain forms is called as catenary. Catenary is different from parabola. It is not, it has a U shape, but it is not in parabola. It is a U-shaped shape which is called as an catenary. So using the principle, variational principle, for which we are given integral I to be extremum, that means it has a maxima or minima value, we can solve what path or what curve, what will be the shortest distance that must be followed using this expression. I hope students, you can solve many more such problems. Thank you students for watching.